Learn like a pro.
Welcome to the Explainer. What if I told you there's a simple blueprint, like an architectural plan, that describes every single interaction in the universe, every push, every pull, every single jump? Well, today, we're going to build that blueprint together so you can understand the fundamental forces that govern all motion.
All right, let's kick things off with a classic physics puzzle. Take a look at this apple just sitting on a book. Okay, so the Earth is pulling the apple down with gravity, right? And the book is pushing the apple up with what we call a normal force. These forces are equal, and they're opposite. So that's got to be an example of Newton's third law, doesn't it? Well, that's exactly what a student named Susan thought, but her teacher told her she was wrong. And this very simple picture, believe it or not, hides one of the most common traps in all of physics.
So who was right? The teacher was, absolutely, and understanding why really unlocks this whole concept. See, the forces on the apple, gravity pulling down, the normal force pushing up, they are perfectly balanced. They cancel each other out, the net force is zero, and the apple doesn't go anywhere. That's a textbook example of Newton's first law. The third law, well, that's about something completely different. It's about a two-way street between two separate objects.
To make sure you never fall into this trap again, we need to get to the core logic of Newton's third law. It's not just some catchy phrase like equal and opposite. No, it's an entire architecture of how things interact, and it rests on four, you could say, unbreakable pillars.
So here's the absolute heart of the idea. Forces are never a one-way street. They always, and I mean always, come in pairs. Just look at A and B here. If body A pushes on body B is, at that very same instant, pushing back on body A with a force that is exactly equal in strength and perfectly opposite in direction.
And this is a great way to visualize those four pillars. Number one, forces always come in pairs. You get an action, you get a reaction. Two, their magnitude, their strength, is always exactly the same. Three, they point in directions that are 180 degrees opposite. And pillar number four, this is the big one, the one that trips everyone up. They act on two completely different objects or targets. Let's apply this to something simple, a contact force. We've got a ball sitting on the floor. Okay, so the floor pushes up on the ball, we can call that F sub FB. And at the exact same time, the ball is pushing down on the floor, that's F sub BF. You see the two targets? The ball and the floor. The forces are equal, they're opposite, and they're acting on two different things. That is a perfect action-reaction pair.
And what's really cool is this same logic works even for forces that act at a distance, like gravity. It is a two-way interaction. We all know the Earth pulls the ball down, but here's the mind-bending part. The ball is also pulling the Earth up with the exact same amount of force. Now, the only reason the whole planet doesn't come flying up to meet the ball is because its mass is just astronomically bigger. But the forces themselves, a perfect identical pair.
So, now that we have the principle down, how do we actually, use it to solve problems? We need a tool. We need a blueprint for visualizing and calculating these forces, especially when things start to get a little complicated. And that tool is called the free body diagram.
So yeah, this tool is the free body diagram, or FBD for short, and its whole job is to strip away all the visual clutter, all that environmental noise, in three simple steps. You start with the real-world situation, then you mentally isolate the one object you want to analyze, and finally, you draw a really simple abstract diagram that shows only the forces acting directly on that one object. And the anatomy of one of these things is just beautifully simple. We just use a box to represent our object, then from the center, we draw arrows pointing out for every single force that's acting on it. This lets us cleanly break down all the forces into their vertical and horizontal parts so we can figure out what the object is going to do.
Now, when you start building these blueprints for yourself, there is one golden rule. And it's so fundamental that if you break it, the whole model just completely falls apart.
And here it is. You must never, ever draw a Newton's third law action-reaction pair on the same free body diagram. It is without a doubt the single biggest mistake people make, because it completely violates the entire purpose of the tool itself.
Just think about it for a second. The whole reason we make an FBD is to isolate the forces on one single object, to see if those forces are balanced or not. But an action-reaction pair, by its very definition, acts on two different objects. So putting both of those forces on one diagram is, well, it's a fundamental contradiction. It just doesn't make sense.
All right, so let's see this blueprint in action. Let's take our new tools, our real understanding of the third law, and our FBD method, and use them to deconstruct a more complex system and make it totally manageable.
So on the left, you see the complex reality. A pulley system, two different masses. Looks a little messy, right? But on the right, that's our deconstruction. We just make two separate, really simple FBDs, one for the 5 kilogram mass and another one for the 8 kilogram block. This lets us clearly map the forces on each part, all by itself, and then we can solve for the motion of the entire system. This whole process, from identifying the forces to mapping them out correctly, can actually be boiled down into a really simple but incredibly powerful checklist that'll keep you from falling into any of those common traps.
So here it is. This is your 4-step blueprint for basically every problem. First, verify the pair. Ask yourself, are these forces a real Newton's third law interaction? Second, check the targets. Are they acting on two different objects? Third, isolate the system. Draw a nice, clean FBD for the single object you care about. And finally, enforce the golden rule. Never ever put an action-reaction pair on the same diagram.
By mastering this blueprint, you'll go from the confusion of Susan's apple to the clarity of a physicist. It really empowers you to map out that hidden architecture of forces that's all around us. So the next time you see something move, ask yourself, what's the blueprint behind it?